We continue our lecture 5, solving congruences, with example 5. To solve the system of congruences in example 4, first let m equal 3 times 5 times 7 equal 105. Big M sub 1 is m divided by 3 equal 35. Big M sub 2 is m divided by 5 equal 21. And big M sub 3 is m divided by 7 or 15. We see that 2 is an inverse of big M sub 1 equal 35 modulo 3, because 35 times 2 is congruent to 2 times 2 is congruent to 1 mod 3. 1 is an inverse of M sub 2 equal 21 modulo 5, because 21 times 1 is equal to 1 mod 5. And 1 is an inverse of M sub 3 equal 15 modulo 7, because 15 equals 1 mod 7. The solution to this system are those x such that x is congruent to a1 big M sub 1 y1 plus a2 big M sub 2 y2 plus a sub 3 big M sub 3 y sub 3, which is equal to 2 times 35 times 2, 3 times 21 times 1 plus 2 times 15 times 1, or 233 is congruent to 23 mod 105. It follows that 23 is the smallest positive integer that is a simultaneous solution. We conclude that 23 is the smallest positive integer that leaves a remainder of 2 when divided by 3, a remainder of 3 when divided by 5, and a remainder of 2 when divided by 7. Example 6. Use the method of back substitution to find all integers x such that x is congruent to 1 modulo 5, x is congruent to 2 modulo 6, and x is congruent to 3 modulo 7. By theorem 4 of section 4.1, the first congruence can be written as an equality. X is equal to 5t plus 1, where t is an integer. Substituting this expression into the second congruence tells us that 5t plus 1 is congruent to 2 mod 6, which can easily be solved to show that t is congruent to 5 mod 6, as the reader should verify. Using theorem 4 in section 4.1 again, we see that t is equal to 6u plus 5, where u is an integer. Substituting this expression for t into the equation x equal 5t plus 5 tells us that x is equal to 5 times the quantity 6u plus 5 plus 1, which is really equal to 30 times u plus 26. We insert this into the third equation to obtain 30u plus 26 is equal to 3 mod 7. Solving this congruence tells us that u is equal to 6 mod 7, as the reader should verify. Theorem 4 in section 4.1 tells us that u is equal to 7v plus 6, where v is an integer. Substituting the expression for u into the equation x equal 30u plus 26 tells us that x is equal to 30 times the quantity 7v plus 6 plus 26 equal 210u plus 206. Translating this back into a congruence, we find this solution to the simultaneous congruences. X is congruent to 206 mod 210. I'm going to let you read the computer arithmetic with large integers for yourself. And we will now go on to Fermat's little theorem. If p is prime and a is an integer not divisible by p, then a to the power p minus 1 is congruent to 1 mod p. Furthermore, for every integer a, we have a to the p power is congruent to mod p. Furthermore, every integer a we have is a to the p power is congruent to a mod p. Example 9. Find 7 to the power 222 mod 11. Solution. We can use Fermat's little theorem to evaluate 7 to the power 222 mod 11 rather than using fast modular exponentiation algorithm. By Fermat's Little theorem, we know that 7 to the 10 power is equal to 1 mod 11. So 7 to the 10 power raised again to the k power is equal to 1 mod 11 and 222 is equal to 22 times 10 plus 2. We now see that 7 to the 222 power is equal to 7 to the 22 power times 10 plus 2, which is equal to the quantity 7 to the 10 power taken to this 22 power times 7 squared. But 7 to the 10 power is merely 1 mod 5. So now what we have is 1 to the 22 power times 49 is equal to 5 mod 11. It follows that 7 to the 222 power mod 11 is equal to 5. And I'm going to let you read primitive roots and discrete algorithms for yourself.